Today we're going to learn how to perform some nonparametric tests in Stata. And in this tutorial we're going to learn about the sign test and the Wilcoxon signed rank test. So let's jump into our first example and consider the following table, which shows central venous oxygen saturation in 10 patients at admission and 6 hours after admission to the ICU. Now it is hypothesized that after 6 hours in the ICU, central venous oxygen saturation should increase. So we want to test this hypothesis. So the first thing we want to know is, are the data independent or dependent? Now, since we're taking measurements on the same person at admission and 6 hours admission, it's clear that this is dependent data. And so what type of tests are available for this type of data? So previously we learned about the parametric test that's available is the paired t-test. And we also just learned about the sign test and the Wilcoxon signed rank test. Now, what type of statistical test is most appropriate for this data and why? Well, we should probably use a nonparametric test since we have such a small sample size. Also, we have no information from the problem to suggest that the differences are normally distributed. We could also investigate this by creating a histogram of the differences and seeing whether normality holds. But again, we have such a small sample size that we probably use a nonparametric test. So for the sign test, what are the null and alternative hypotheses? Now, the null hypothesis is that the median of the differences are the difference at admission and 6 hours after admission to the ICU. And the alternative is that the median is not equal. The median of the differences is not equal to 0. Now remember, for the paired t-test, we would exchange this median. We would put mean here if this was a t-test, if this was a paired t-test. But it's not. We're doing a nonparametric test, so we're concerned about the median here. So this slide is just to show you how you would perform a sign test by hand, basically. So what you would do is you would get your data lined up over here. You'd get your data at admission, and 6 hours after admission, you'd calculate the difference, and then you'd look at the sign of the difference. So for this example, you count up the positive signs. We have 8 positive signs, and we have 2 negative signs. Now we don't need to do this by hand. We have Stata. So go ahead and open up Stata now. The data set is called cvos.dta. And in the data set, when you open it in Stata, you'll notice there's only 2 variables. Central venous oxygen saturation at admission, that's T0, and central venous oxygen saturation 6 hours after admission, that's T6. Now the sign test command is very simple to remember. It's just sign test. So type in the following command, sign test T6 equals T0. Now let's look at the output. The first thing that Stata gives us is a table of the positive signs and negative signs. Notice that we observed 8 positive signs and 2 negative signs. The 0 category simply counts the number of ties, since if a difference is 0, it's neither positive nor negative. Now the expected column shows us how many positive and how many negative signs we would expect under the null hypothesis. Now remember, the null hypothesis states that the median of the differences is equal to 0. Thus, we would expect approximately equal number of plus and minus signs. Or, to put it another way, the probability that a particular difference is positive is 1/2, and the probability that a particular difference is negative is 1/2. So what we have here is basically a list of 10 either positive or negative signs. So if we consider a plus sign a quote success, then the 10 positive and negative signs can be thought of as outcomes of a Bernoulli random variable with probability of success equal to 0.5, and that's under the null hypothesis. As a result, under the null hypothesis, the total number of plus signs is simply a binomial random variable, with this case n equal to 10, and again under the null hypothesis p is equal to 0.5. Now how do we calculate our p-value? Now it's important to remember the definition of a p-value. It's the probability of observing a test statistic as or more extreme than we actually observed, given that the null hypothesis is true. Now in the book and in the lectures, Marcello gives you a test statistic for large n. They give you a formula to calculate a z-value, and then you can use the standard normal tables. Stata, on the other hand, doesn't like that. They don't assume large n, and they're going to give you an exact, quote, an exact method for calculating a p-value. So I'm going to go over how Stata calculates this p-value. So in our example, the test statistic that Stata gives us is 8. That is, we have 8 positive signs. Thus, something as or more extreme than 8 positive signs would be 8 positive signs, 9 positive signs, and 10 positive signs. Remember, this is a two-sided test, so something as or more extreme than 8 positive signs would be 8 or more negative signs. So if we look down here under two-sided test, gives us the null and the alternative, and here what it's calculating here is the p-value. So probability number of positive is greater than or equal to 8, or number of negative is greater than or equal to 8. Thus, our p-value is the probability of observing 8 or more successes in 10 trials, given that the probability of success is 0.5, plus the probability of observing 8 or more failures in 10 trials, given that the probability of failure is 0.5. That's what Stata is calculating down here. And remember, from a couple weeks ago, we learned how to calculate these values in Stata. And Stata obviously does it for us and gives us a p-value of 0.1094. Thus, if we use an alpha of 0.05, we will fail to reject the null hypothesis and conclude that we do not find evidence that median central venous oxygen saturation is different at admission and 6 hours after admission to the ICU. Suppose that instead of conducting the sign test, we conduct the Wilcoxon signed rank test. Now, which test would have more power? Now, the signed rank test has more power since it incorporates the magnitude of the differences via the ranks. So what we're just using more information, which will give us a better chance of detecting a difference if there is indeed one. So remember, the sign test we just use plus or minuses, but the signed rank test we use plus or minus, and we also rank the magnitude of the pluses and minuses. So let's go ahead and state the null and alternative hypothesis for the Wilcoxon sign rank test. And it's the same. It's exactly the same as the sign test, just that the median of the differences is equal to 0, and the alternative is that it's not equal to 0. So this is just to show you how the sign rank test works. So again, we've lined up our values at admission and 6 hours after admission. We've calculated the difference and we've calculated the sign. Now we need to rank the absolute value. So this one with the rank 1 is the smallest. Number 2 is the second smallest, and so on and so forth till we get to 10, which is the largest difference. So as you can see, the difference between the sign test and the sign rank test is we're going to incorporate this information via the ranks, this rank information. Now again, we don't want to calculate this by hand every time. That's why we have Stata. So let's go to Stata right now. Now the syntax for the sign rank test is again very simple. It's just sign rank, one word. So type in the following command, sign rank T6 equals T0. So now looking at the output, the first thing that Stata gives us again is this table of observed positive and negative signs. And as you can see, Stata also gives us the sum of the ranks. So if we had, remember all those ranks we had previously, if we summed up the positive ones and summed up the negative ones, we would get the sum of the ranks for the positive signs would be 50, and the sum of the ranks for the negative signs would be 5. And remember, similarly to the sign test, we would expect the sum of the ranks to be the same for the positive signs and the negative signs. So we'd expect 27.5, the sum of the ranks to be 27.5 for the positive signs and 27.5 for the negative signs. So we can just, again, looking at the output, it's not important to know about these adjustment for ties and adjustments for zeros. But we do want to look at here is the z value, 2.293, and we get our p-value here, which is 0.0218. So as we can see here, we have if we use an alpha equals 0.05, our p-value is less than 0.05. Therefore, we can reject the null hypothesis. Now, if you remember, the p-value for the sign test was 0.10. So as you can see, by incorporating the ranks, we have more power to detect a difference. And in this case, we went from not rejecting the null hypothesis to rejecting the null hypothesis. So now to summarize, we learned about the sign test and the Wilcoxon sign test. And remember, the sign test uses the plus or minuses of the differences only. It's not used very often simply because the sign rank test is basically the same thing but has more power. And again, remember, for small n, we can use the binomial distribution to calculate p-value for d. Remember, d is just simply the number of positive signs. Now the Wilcoxon signed rank test, it's the non-parametric analog to the paired t-test. It has more power than the sign test since it incorporates the magnitude of the differences via the ranks, and should be used, if you have a choice between the sign test or the sign rank test, you should use the sign rank test. Remember, the Stata commands are very simple. It's just sign test and sign rank test, so those are very easy to remember.